to talk to you today. So I'm going to talk about semantic representations of actions and state. And actually, I'm first going to start by arguing that that's the sort of core of the entire AI problem. You know, just for sheer ambition. So I'm I'm a roboticist because I want to solve the AI problem, and I don't think that that's a coherent or well-formed question without thinking about robots. So you're a robot and I'm a robot, and every person that we know is a robot. We're not computers, right? There aren't any brains in nature that aren't contained in bodies. And so I think it's crucial when we think about a single agent that is able to solve any problem that we start to think about how we could build a single and generally intelligent robot that's able to solve any problem. And I'm interested in that sort of question, which is now called AGI, but used to just be called plain old AI, where we're interested in building a single agent that's able to do just about anything moderately well. Okay, so intelligence is the ability to do not to do a single thing extremely well, because only one person out of n can be the best person in the world at something. Actually, humans are interesting because they can do almost anything reasonably well. And when we look at what happens when we try and build a robot to do that, we see that there's a dilemma built in that's not obvious in the rest of the AI literature, but is obvious when you think about robotics. So when you are posing a bunch of problems in the rest of AI, what you get, it's sort of assumed that you get the formulation for free. Okay, so if you want to play Go, someone will set up an MDP where the state space looks like a 19 by 19 array with one of two types of pieces of two colors. And every legal action that you can take is a move to put down a piece in a particular place. And then they'll give you an objective function that says maximize the number of wins. And then the agent will just sort of know that that's an MDP, so that reinforcement learning is the right thing to do. And then if it's doing classification in an image, it just gets an image that's kind of cropped and rotated to the right spot. That's its input, and its output is labels. And then we just get an objective function that minimizes errors. And the agent just knows magically that that's a classification problem. Okay, and that's cheating. So every time you see that happen in an AI setting, and people claim to be talking about general intelligence, something should go off in your head, because what happens when we think about doing that in a robot is we don't get those representations for free, right? There's no reason at all to believe that a robot goes around in the world having a pre-prepared representation for chess. Instead, it has to solve all the problems in this like wildly overpowered state and action space, right? This wildly overpowered sensing and action space, because it has to be overpowered, because if you need to be able to solve all the problems with it, then it needs to be extremely overpowered for any individual problem. Okay, so we call this the sensorimotor dilemma. And so we're going to think about how you might resolve that. And in my lab, we've adopted this thing called the ego process. In robotics, it's just the robot sensorimotor loop, but in AI, you have to give it a name because it's weird. And the idea is that the robot is going to be, is that we're going to kind of form like a sort of a kind of like Uber interaction with the world, which looks like a POMDP, where the robot is interacting with the world, not any particular task. It can take actions. It can receive observations, which are extremely rich. And it's going to be given task after task. That's how it's going to be general purpose by some human drawn from a distribution of reward functions. So the reward function is going to describe the specifics of a particular task, but it has to solve them all in the same state and action space. And so what we'd like to do is we'd like to transform that like wildly overpowered state action space to a state action space that actually makes sense for a particular problem, right? And once we can do that, then we can think about importing all the existing decision-making things from AI. And that seems like a mildly crazy, wildly out of control thing to imagine doing. But actually, when you formulate things in the reinforcement learning setting, this can kind of be well defined, right? So the way that we've chosen to formulate it is to say that you've got an MDP, which is states, actions, rewards, transitions, and gamma. And so that's a particular task reward, and the state in the action space of the robot's like wildly overblown state and action space. And we'd like to be able to compose a much smaller, much tinier task relevant state and action space, so that if you're doing something like playing chess, suddenly you're in the state and action space of a chessboard, right? And it turns out that these two things are both well studied in reinforcement learning, but typically in isolation. So the first one is called state abstraction. You'd like to take a very high dimensional state space and shrink it down to a small task relevant state space. And the second one is called action abstraction. We'd like to do the same for your actions. You'd like to build high level skills that let you do things like move a chess piece instead of kind of twitch your motors. Okay. And the trick is that you have to do these things in combination. You have to do them both at the same time, or they have to be built in some way to be compatible, because there's no reason to believe that if you did them separately, they would just happen to form a well-formed decision process. So in my lab, we've chosen to sort of go what we call action first, which is that we've chosen to build the action abstractions and then the state abstraction to support those action abstractions. Now, what I want to point out here very quickly is that you can view almost all the classical decision-making paradigms of AI as special cases of that abstract MDP. Okay, so if the state space is discrete and the action space is discrete, and you've got a deterministic transition function and you've learned a good model of it, then you can solve that problem with search, right? You can deploy a star. And if the transition function looks kind of adversarial to you, then you might want to treat it as an adversarial transition function, and you could do something like alpha beta pruning. And if the state space and the action space are factored and the transition function is deterministic and you've got a good transition function, then you're in classical planning land and you can deploy something like PDDL or strips. And if it's the case that the transition function ends after a single execution always, and you've got a continuous state and a discrete action space, then that's called a banded in reinforcement learning. And if you have demonstration for that banded, what you have is classification. Okay, so you can actually build like a sort of decision tree where you take all the kind of decision-making things of AI and you say, hey, if the agent has a rich representation of that, of the task-specific representation that it's built, and it can look inside that task-specific representation, understand its properties, then it should be able to kind of roll out the right generic existing sort of AI paradigm to solve that problem. So that's what we'd like to be able to do. And then the idea is that we're going to kind of on a task-specific basis, learn these task-specific representations, roll out the right generic decision-making paradigm, and that's how we access the rest of AI. Like that's how we unify the rest of AI with this kind of a low-level single agent process. That's our take on general AI. So the question is, how are we going to do this? And for this talk, I'm just going to assume that we have the high-level actions available to us. I wrote my PhD on how to find them. Lots of people have, and we're going to put that question aside for now and assume that they're ready. And we'd like to be able to build a framework that accounts for, okay, if I'm going to build an abstract state representation, a symbolic representation, I need to tell how it's grounded. I need to know when it's discrete and continuous, when it's deterministic, when it's stochastic, and I need to have an agent able to learn it autonomously. So the way that we approach this is what we call a constructivist view, which is we said, okay, let's formalize the computational question that we're going to ask, and then let's like build a representation so that it's able to answer that question by construction. So the question that we focused on first was to say, okay, what happens if we want to plan? What's the simplest question that we could ask in planning? Let's say that you have a start state in a low-level state space, and you have a sequence of motor skills that you want to execute. So the simplest question that you could ask of a planner is, can I definitely execute that with probability 1 or not? And then we can think about what abstract entities you need to be able to have to answer that question. And it turns out that you need one set and one operator for every motor skill. So the set is the preconditioned set. It's the set of states from which you can execute that motor skill. Here you see the set of states from which you can push that red button. And we need what we call the image operator, which is if I'm in a set of states and I execute a motor skill, what's the set of states I could land up in with non-zero probability? Okay, so if I'm that robot and I run a go to the right skill, and because the world is stochastic and all that other stuff, there's a set of states I may land up in. And you can sort of write a proof that says if you started at a set of state Z and you wanted to know if the first motor skill was executable, you could say, well, yes, it is, if and only if that set of states was inside the precondition of the first motor skill. And then you could compute the image of executing that motor skill from that set. And then if you wanted to ask for the second motor skill, can I execute that? You could say, yes, if and only if the image of that motor skill is inside the precondition of the next skill. And you can actually write a proof for any sequence of skills in this format, and it contains only that image in that precondition and the start state Z. So if you're able to compute those quantities, then you can compute this answer for any sequence of skills that you might wish to execute. So that's a sort of sketch of why this set and this operator are necessary and sufficient. They're a sort of complete vocabulary. And then what we're going to do is we're going to assign high-level states, abstract states, to those sets. So we're going to say I'm going to start in a set of states. That's the grounding set for a particular abstract state. And then if I want to know if I can execute an action from that abstract state, I'm going to say yes, only if that abstract state is a subset of that action's initiation set. And I'm going to add an arrow to my symbolic representation. And then the state that you land up in next is the one that has a grounding corresponding to the image of that transition. And then because this is necessary and sufficient, you can throw away the downstairs, the grounding, and you can just plan with the top abstract representation. And it's a sound and complete representation. So if there is a plan in the symbolic representation, then there is one in the grounded world. And if there isn't one in the symbolic representation, there isn't one in the grounded world. So that's nice, but there might be infinitely many of those abstract states. So here's a condition under which there are only a finite number of them. If you can break your skills down into sub-skills such that when you execute them, it kind of doesn't matter which low-level state you started with, you land up in roughly the same set of states. So we call this a sub-goal option. Then you can swap that image operator for just an effect operator that doesn't depend on where you start. And now this is never true for any skill, but very often it's approximately true. It's close enough for a model. And if you do that, then you can build a finite representation where the only thing you care about is whether the effect set of one skill is inside the initiation set of another skill. Okay, and then you can build a graph. You can take your representation, build a graph, and apply a star, and that graph representation is provably sound and complete. Of course, in robotic case, that's kind of unrealistic, right? So a more realistic setting is what happens if you've got a lot of state variables and you execute a motor skill and you only change some of them. So imagine that you're this robot and you're picking something out of a cupboard. You change the position of that object in your hand and maybe the robot's base, but not like whether the door is closed or not. Okay. So this is a sort of factored abstract subgoal action that changes, that has the subgoal property only for a few of the state variables and leaves the rest unchanged. And it turns out, and I'm going to skip the math, but it turns out that if that's what you have, what you get is strips. The representation that comes out is a factored strips-like representation, and that's the sort of necessary and sufficient thing, and it's discrete. Okay. Another way in which that's unrealistic is there's nothing ever executes with probability 1 of the robot. So what we did is we upgraded this representation to the probabilistic setting. So instead of having a precondition set, we then built a precondition, a probabilistic classifier. So instead of saying, can I run this action from a state, you say, what is the probability that I can run this action from a state? And we changed that image operator, which says, what's the set of states I could land up in? We changed that to what's the distribution of states I might land up in? That's a density estimator. And if you do those swaps, then you can prove that this is necessary and sufficient for computing the probability with which you can execute a plan. And also, probabilistic classifiers and density estimators are things we know how to do in machine learning. There's all this wonderful toolkit available to us. So we can actually just execute motor skills in the world, apply probabilistic classification techniques and density estimation, and learn these representations from scratch. So we built a system that learns symbolic representations by executing the skills and getting some data. And the data look like, I'm in a high-level state, a low-level state, I execute an action, I get a new low-level state and a reward. We use that for training the density estimator. And then I'm in a low-level state, which of my motor skills can be executed from here? And we use that to train a probabilistic classifier. And the main complexity here is just kind of breaking the motor skills down so that they're approximately sub-goal. So let me show you that working on a real robot. So here's a task that we designed. On the left, you can see a sketch. On the right, you can see some videos, some photos. So here I just hand built the motor skills, right? I just coded them from scratch myself. And there's a robot, and I built a navigation skills that can move it from a cupboard to a cooler. So there's a cupboard, you can see the bottom right, it's blue, and a cooler top. Sorry, the cupboard is in the top left, and it's wooden, and the cooler is in the bottom right, and it's blue. And it can navigate between those two places, and it can open and close the cooler and the cupboard if it's got both hands available to it. And then there's a little switch, which you can see just slightly to the right of the cupboard. And it can open and close the switch if it's standing in front of the cupboard. But there's a trick, which is that if you open the cupboard, it blocks physical access to the switch. Also, when the switch is on, it switches on a light inside the cupboard that's very bright. I had to find a very bright light bulb, such that it kind of whites out the robot's perception. And therefore, it can't manipulate anything in the cupboard. It's too bright for it to be able to interact with the stuff in the cupboard. And then there's an object, you can see the robot holding it in the top right. It's just a green bottle that could be in the cupboard or could be in the cooler. The robot can pick it up if it can see it, and it sort of holds it up here when it's picked it up. So we just, and of course, as I described that to you, you could write down a small MDP describing this thing. You could say, well, the cupboard needs to be open or closed, or the cooler needs to be open or closed, or you could be holding an object or not. But that's cheating, right? We want the robot to be able to learn that for itself from scratch. So we're going to give it input that looks like raw sensorimotor data. In particular, we're going to start off with its pose in the map, X, Y, theta, a voxelization of the whole room. I've just cut out the cooler here, but it's the whole room that we give to the robot, and its raw joint positions. And we're going to ask it to learn that high-dimensional state space representation from data. So here's the robot just executing motor skills in the world. It's opening and closing the cupboard, it's turning the switch. You can see the lights on, opening and closing the cooler. There's an object inside the cooler, so it'll pick it up in a bit. There we go, picking it up and putting it down. It can turn the switch when it's holding it, but it can't open the cupboard. And we have to execute about 160 such actions, which takes a couple of hours in order to be able to gather sufficient data to learn an abstract representation of this task. Okay, so once the robot has done all of that, out pops an abstract representation that looks like this. So the top is the abstract representation. It's a text file, so it's inarguably a symbolic representation. And what it does is it names some symbols. It says if you want to navigate to the cooler, symbol 1 has to be true. Afterwards, symbol 0 is true, and symbol 1 is no longer true. And these refer to distributions over states. So these particular ones refer to the distributions over the robot's pose in the map. So I've drawn some samples from those distributions and visualized them. In the bottom left, you can see symbol 0. Symbol 0, if you remember where the cooler was, that's like when you're standing in front of the cooler and facing it. And symbol 1 is roughly when you're standing in front of the cupboard and facing it. So what the robot's learned is if you want to navigate to the cooler, you should be standing in front of the cupboard. And afterwards, you won't be standing in front of the cupboard, you will be standing in front of the cooler. So it's discovered that discretization, it's discovered those symbolic representations, it's discovered their groundings, and it's able to learn a symbolic rule that tells you how to move between them. All of that just from the raw data. Here's a more interesting symbolic representation. If you want to open the cupboard, you have to be, symbol 1 has to be true, you have to be standing in front of the cupboard. Symbol 3 refers to distribution of the robot's joints. And if you recall, when it's holding something, its hand's sort of up here. So that means it's not holding anything. And then symbol 4 is a distribution over the voxels. And I've just cut out the cupboard here. And you can see that the switch could be on or off, and there's a bunch of compression noise and stuff, but the cupboard's closed. And then afterwards, if you execute the skill, the cupboard will be opened, and it will take about 67 seconds to execute that skill. Okay, and again, the cupboard open, all these discretizations, all these symbolic representations, learn from scratch. We didn't program that into the robot, we just let it learn them, and it learns them because those are the symbolic representations it needs to be able to execute its motor skills and plan with them. Okay, so I'm going to skip those because we're running out of time, but I wanted to show you the robot planning. So here's the robot. I've put it in front of the cooler and put the object inside of the cooler, and I've left the light switch on. And then I asked it to plan to solve this task. And I just gave it the text file. And of course, it planned to solve this task in 4 milliseconds because the task is trivial, right? It's a ridiculously small task once you're in that representation. So what it does is it opens the cooler, but it doesn't pick up the object, because if it did pick up the object, it couldn't open the cupboard. So it moves to the cupboard, but then it doesn't open the cupboard because if it did, it couldn't turn the switch. So first it turns the switch. There we go. Then it opens the cupboard. Then it goes back to pick up the object and put it in the cupboard. Now, that's not surprising. That's what classical planning classically does, right? What's interesting about this is not that if you give a classical planner a representation like that, it solves it easily. What's interesting is that this robot learned that representation from scratch, right? Essentially from pixels. And then it was able to use it to plan. And those grounded symbols were an accurate model of what was happening in the world. And so it was able to build this symbolic representation. So there it's going to put the, there's little delays here. The delays are because I'm bad at doing vision. They're actually for merging the point clouds, not for planning. I also asked it to sort of clean up, so it's gonna close all the close the cupboard and the cooler and come back to a rest position. And subsequent to that work, or this, this work goes back to 2014. We've now applied this in something like 12 different domains. I think 4 or 5 of them are real robots. Knuckle will talk a little bit about one particular collaboration that we had involving language. We've also done a lot of work on portable symbolic representations and representations that support generating suggested repairs and active learned representations and hierarchies and all that stuff. So it's kind of getting well developed. And if you're interested, please have a look at some of these papers. Okay, so just to conclude, key takeaways. I think that learning abstract representations, learning these semantic representations, like that's it. That's like the big key thing that we're missing. Rodney Brooks once said, if you're in a field that's not working, you should ask what assumption the field is making that's so basic they don't even know it's an assumption and it's broken. And for the rest of AI, that assumption is that agents arrive with these well-formulated problems that are in nice, happy problem classes, and those problems are just gifted to them. And when you're already thinking about an agent being in that box, it doesn't make sense to think about a general purpose agent because your agent's an agent for playing chess, or it's an agent for playing tic-tac-toe, or an agent for doing pole balancing. But it only makes sense to think about a general purpose agent that's a robot, but then that robot has to bridge that gap, has to learn those symbolic representations. And the way to figure out how to do that is to ask the math question, what are those representations for? Okay. So we've built such a framework and we think it's very exciting, but of course there's a bunch of other people doing similar things. And the end takeaway is that you're going to have agents first learning how to frame a problem, then applying generic solutions to them, whether it be adversarial search or a SPAR or policy search when the states and actions really are continuous. Okay, that's my presentation. Thank you.